Hello all, welcome to this video on Operating System Lab. Today I'll be talking about SJF scheduling in OS and its implementation in C. We'll start by looking into what SJF is. This algorithm associates with each process the length of the process's next CPU burst. When the CPU is available, it is assigned to the process that has the smallest next CPU burst. If the next CPU bursts of two processes are the same, then FCFS scheduling is used to break the tie. Note that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm because scheduling depends on the length of the next CPU burst of a process rather than its total length. Also known as the shortest job next SJN or shortest process next SPN, it is a non-preemptive algorithm. Shortest job next is advantageous because of its simplicity and because it minimizes the average amount of time each process has to wait until its execution is complete. However, it has the potential for process starvation for processes which will require a long time to complete if short processes are continually added. High response ratio next is similar but provides a solution to this problem using a technique called aging. The disadvantage of using a shortest job next is that the total execution time of a job must be known before execution. While it is impossible to predict the execution time perfectly, several methods can be used to estimate it, such as the weighted average of previous execution times. Multi-level feedback queue can also be used to approximate SJN without the need for the total execution time oracle. Shortest job next can be effectively used with interactive processes which generally follow a pattern of alternating between waiting for a command and executing it. If the execution burst of a process is regarded as a separate job, the past behavior can indicate which process to run next based on an estimate of its running time. Shortest job next is used in specialized environments where accurate estimates of running time are available. As an example of SJF scheduling, consider the following set of processes with the length of the CPU burst given in milliseconds. For process P1, it is 6, P2 is 8, P3 is 7, and P4 is 3. Now, using SJF scheduling, we'll schedule these processes according to the following Gantt chart. So, you can see that the process P4 is executed from time 0 to 3 and process P1 is executed from time 3 to 9. Then we have process P3 from 9 to 16 and P2 from 16 to 24. The wait time is 3 millisecond for P1, 16 millisecond for P2, 9 millisecond for P3 and 0 millisecond for P4. Thus the average waiting time is sum of this divided by 4, which is 7 millisecond. By comparison, if we were using the FCFS scheduling scheme, the average wait time would have been 10.25 milliseconds. The SJF scheduling algorithm is probably optimal in that it gives the minimum average waiting time for a given set of processes. Moving a short process before a long one decreases the wait time of the short process more than it increases the waiting time of the long process. Consequently, the average waiting time will decrease. The real difficulty with the SJF algorithm is knowing the length of the next CPU request. For long-term job scheduling in a batch system, we can use the process time limit that a user specifies when he submits the job. In this situation, users are motivated to estimate the process time limit accurately. Since a lower value may mean faster response, but too low a value will cause a time limit exceeded error and require resubmission. SJF scheduling is used frequently in long-term scheduling. Although SJF algorithm is optimal, it cannot be implemented at the level of short-term CPU scheduling. With short-term scheduling, there is no way to know the length of the next CPU burst. One approach to this problem is to try to approximate SJF scheduling. We may not know the length of the next CPU burst, but we may be able to predict its value. We expect that the next CPU burst will be similar in length to the previous ones. By computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. The next CPU burst is generally predicted as an exponential average of the measured lengths of the previous CPU bursts. The SJF algorithm can either be preemptive or non-preemptive. The choice arises when a new process arrives at the ready queue while a previous process is still executing. The current CPU burst of the newly arrived process may be shorter than what is left of the currently executing process. A preemptive SJF algorithm will preempt the currently executing process, whereas a non-preemptive SJF algorithm will allow the currently running process to finish its CPU burst. Preemptive SJF scheduling is sometimes called shortest remaining time first scheduling. Now we will see an example for preemptive SJF scheduling. Here we have four processes P1, P2, P3, P4 along with its arrival time and burst times. So if they arrive at the ready queue at the times given here and they need the indicated burst times, the resulting preemptive SJF schedule will be as shown in the Gantt chart here. So P1 from 0 to 1, P2 from 1 to 5, P4 from 5 to 10, P1 from 10 to 17 and P3 from 17 to 26. Now process P1 started at time 0. Since it is the only process in the queue at that time, now P2 is arriving at time 1. Now the remaining for process P1 will be 8 minus 1, 7 millisecond. Now that 7 is still larger than the time required for process P2 which is 4. So P1 will be preempted and P2 is scheduled which is shown in the Gantt chart here. Now the average wait time for this example will be the waiting time of all the four processes, which will be, for example, taking the case of P1, it will be 10 minus 1. Similarly, we take it for P2. So P2 has the arrival time 1. It is actually starting its execution at 1. So it's 1 minus 1. And then we have it for P3. P3 arrived at time 2. So it actually started execution at 17. 17 minus 2. And for P4, it is 5 minus 3. So summing it up and dividing by 4, we'll get the value 26 by 4, which is 6.5 millisecond. Now non-preemptive SJF scheduling would result in an average waiting time of 7.75 millisecond. This is the actual example used in the program that will be discussed after some time. So here I have assumed that there is no IO burst. So there only will be CPU burst. And there are 5 processes given along with the arrival time and burst time. From these two values, the following values have been calculated, which is the start time, completion time, turnaround time, wait time, and the response time. So in order to find out these values, first we'll look into the Gantt chart for this process set, how it is looking like. So when we scan through the arrival times and the burst times, we'll see that the first process is arriving only at time 2. So from time 0 to 2, the CPU will be idle. So this is marked as the idle time. Then at time 2, we see that we have two processes coming up, P0 and P1. Also, their burst times are equal. So what happens is, if the arrival time and the burst time are the same, we'll go forward with the one having the lowest process ID. Here it is P0. So P0 is executed, which has the burst time 2. So it will take up the CPU from time 2 to 4. Then we have P1 with a burst time of 2. But by now the time is 4. By then we'll have both P3 and P2 which has arrived with the burst times 5 and 3. So when we compare these three, still 2 is the lowest value, so P1 will be executed. Now after its execution the time is 6. Now by then the process P4 has also arrived at time 5. Now we see its burst time is 4. Now these three processes remain. From these, P2 has the lowest burst time, so that will be executed till time 9. Then we have P4 with a burst time of 4 executed till the time 13, and then we have P3 which is executed till time 18 with a burst time of 5. Now from this we can calculate the start time of each process. So P0, when we check that, we see the actual start time is 2. For P1 it will be 4. P2 it will be 6. P3 it is 13 and P4 it is 9. Now the completion time of these processes also can be seen from this chart. So for P0 it is 4, P1 it is 6, P2 it is 9, P3 it is 18 and P4 it is 13. So from these values we will be able to calculate the turnaround time. So turnaround time is completion time minus the arrival time. So subtracting this I'll get 2, 6 minus 2, 4, 9 minus 4, 5, 18 minus 3, 15 and 13 minus 5, 8. Similarly, the wait time can be calculated by the formula turnaround time minus the burst time. So it is 2 minus 2, 0, 4 minus 2, 2, 5 minus 3, 2, 15 minus 5, 10 and 8 minus 4, 4. The response time is given by start time minus the arrival time, which is 2 minus 2, 0, 4 minus 2, 2, 6 minus 4, 2, 13 minus 3, 10 and 9 minus 5, 4. Now we have all these values. We'll be able to calculate the average of all these. So the average turnaround time, summing this up and dividing by 5, we get 34 by 5. Average wait time is 18 by 5 and average response time is again 18 by 5. Also we can calculate the CPU utilization and throughput. Now the formula for CPU utilization is the total time here subtracted from it is the idle time, and this is again divided by the total time, and if you multiply it by 100 you will get it in terms of percentage. So here the total length is 18, idle time is 2, so 18 minus 2 by the total time 18, that is 16 by 18. If you multiply it by 100 you will get it in terms of percentage. Then we have the throughput. Now throughput is the total number of processes divided by the schedule length. So total number of processes is 5. The schedule length will be the total time minus the idle time. So 18 minus 2. So the value will be 5 by 16. Now we'll see the logic of the program that is implemented here. So here, first of all, the input is taken in the form of arrival time and CPU burst time of each processes using a loop with a limit n. N is the number of processes. Then they are sorted based on their arrival time. Now if the arrival time is the same, FCFS is used. Now if both the arrival time and the burst time are equal, then I'll choose the process with the lowest ID. Then initially the first process is taken, that is the one with the minimum burst time. Then its completion time is calculated first of all. Then that particular process will be set as the least value. Then comparison is done between the arrival time of Pi plus 1 and the completion time of Pi plus 1. Now checking if the arrival time is less than or equal to the completion time of the process. Now if that is the case, then again this process and the process which is set as least will be compared based on their burst times. Now, if Pi plus 1 will have a shorter burst time, then it will be the new least, or this process will continue to be the least one. Also, in another loop, the arrival time of Pi and the completion time of Pi minus 1 is compared. Now, if it is less than or equal, then the wait time will be the completion time of I minus 1, or the wait time will be calculated based on the arrival time of Pi. Then in another loop that is outside this current loop, the completion time will be calculated, which is wait time plus the burst time. Now this is the program that I have implemented. This is a sample of the output of the program. Here the number of processes is asked. It is 5. Now this is the same example that I have discussed before. The arrival and the burst time of each process is given as input. Then it will list out these values based on it, and the Gantt chart is displayed here along with the average turnaround time and the average wait time. Now let us look into a demo of the same. This is the program that I showed before, the one for non-preemptive SJF scheduling. Then I compile the program. After that, I run the program. So it asks for the number of processes, it is 5. The arrival and the burst times 2, 2, 2, 2, 4, 3, 3, 5, and 5, 4. So this is the expected output. That's all for now. Thank you for watching.